Everybody's just in time. All right. So today we are learning permutations and combinations. So we're finishing out probability with permutations and combinations. So we'll start with a permutation. Okay. So a permutation is an arrangement of objects in which order is important. And so in order to do, so permutations is saying, like if we lined up at the door, the order in which we line up matters. Does that make sense? Okay, so order matters here. And in order to do permutations, we have to do what's called a factorial. Have y'all ever heard of a factorial before? Mm-hmm. You have? Okay, cool. So the factorial is the product of positive integers less than or equal to n. So what this means is if I have a number n factorial, we would do this by saying, okay, n, and then we'll multiply it by the one number less than n, and then a number less than that, and a number less than that, so on and so forth, until we get all the way down to 2 and then to 1. So we're basically multiplying it by everything that's lower than it. Does that make sense? So 5 factorial would be 5 times 4 times 3 times 2 times 1. Are we okay there? Yeah. So what we're doing is when we're finding a factorial, we're multiplying that number by itself and then every number less than it. So 5 factorial, we would do 5 times the number less than that, 4, times the number less than that, 3, times the number less than that, 2, times 1.
And you'd stop at 1.
You'd stop at 1. Because we're only worried about positive integers. Does that make sense? All right. And then the other one, which we do need to kind of specify, that 0 factorial is 1. I know that that's a little confusing, but 0 factorial is technically 1. That's the rule.
So you would say like the number is 3, you do n minus 3, n minus 2, n minus 1, and then n minus 0 for the 1.
So n is 3 there. So when I'm writing this, I'm saying like I would do 3 times 3 minus 1, which would be 2, right? Times 3 minus 2, which would be 1. And this would be where I stop there. Does that make sense? Because we're down to 1. Okay. So let's do some stuff with it. So Shanice and Renee are members of the lacrosse team. If 20 girls on the team are each assigned a jersey number 1 to 20 at random, what is the probability that Shanice's jersey number will be 1 and Renee's will be 2? So the first thing we need to determine is the total number of outcomes. Okay, and the total number of possible outcomes is going to be what we call 20 factorial, right? There are 20 different jersey numbers. Do we all understand that? So when we pick the first jersey, we have 20 options, right? But then that jersey gets taken up, and on the second time, how many options do I have then? 19, right? Because one jersey's taken away, so now I only have 19, right? Okay, I sign that jersey. And then how many choices do I have after that? 18. That's why it's 20 factorial. Does that make sense? Because we're going to be doing 20 times 19 times 18 and so on and so forth. Are we all okay with that? Okay. So we want to find the probability, though, that we pick Shanice for jersey number 1 and Renee for jersey number 2. Okay, so what this means is our first 2 jerseys are picked for us, right? So how many options will I have after that? 18, right? So the options after that would be 18 factorial if I pick those first 2. And to get the probability, we take that over the total number of outcomes possible. Now, you can type all this into your calculator, but you're going to start to get some really, really big numbers. What we can do instead is 20. I can say, okay, 20 times 19, right, times 18 factorial. Those are the same things, right? Because 18 factorial is just saying times 18 and everything below it. Do we understand that? So then what's going to happen? That'll make our life easier. Yeah, but what's going to happen when we divide? The 18s will cancel. The 18 factorials will cancel, right? Because if I'm doing 18 times 17 times 16 and so on and so forth in the numerator, and I'm doing it in the denominator, they're going to end up canceling out. So really my probability is going to be 1 over 20 times 19. So then we just need to do 20 times 19. So what would that be? $380. So we have 1 out of 380 chance of that happening. Okay, so can I go? Okay. So the number of permutations of n distinct objects taken r at a time is denoted by this. So we call this n, it's a permutation, and we're choosing a certain number of things. Okay, so n is the total number of things that we have. R is how many we're picking. So saying like, all right, I have you guys, you're a class of 22, and I pick 4 students. Our n would be 22. What I'm picking, r would be 4. Does that make sense? Great talk, guys. Okay. So it's going to be n factorial over n minus r factorial. Okay. Now, this is referencing all possible outcomes. This is not probability. Okay, so when we're doing this, we're saying this is our possible outcomes. We're not saying this is a probability of an outcome occurring. What we did previously, remember, we do like how many outcomes we want that work out nice for us over the total number of outcomes possible. Does that make sense? Okay. So when I say the number of permutations of 5 objects taken 2 at a time, again, I have 5 objects and I'm taking 2. So that's how we would write it. So we'd solve this by saying, okay, n factorial, which is 5, over n 5 minus r factorial. Okay, bless you. So this is going to be 5 factorial over what? 3 factorial. Okay. And again, do we understand that I can write this 5 factorial? I want to rewrite it so that I could get the 3 factorial to cancel, right? So I can write that as 5 times 4 times 3 factorial. So now what's going to happen? Okay, because 5 factorial is, don't write this, 5 times 4 times 3 times 2 times 1, right? That is what 5 factorial is representing. 3 factorial is 3 times 2 times 1. So we see that these are the same things, right? So that's why I can do 5 times 4, and I can replace this with 3 factorial. Does that make sense? It just helps us to kind of simplify it. Okay? So, okay, so now we're writing this. These are going to cancel. And so really I'm just getting 5 times 4. So how many outcomes can I have? 20. If I have 5 objects and I take them 2 at a time, I've got 20 different outcomes. Alrighty. Can I go? All right. So a class is divided into 2 teams made up of 15 students. Each team is directed to select team members to be officers. If Sam, Valencia, and Deshawn, I don't know, are on a team and the positions are decided at random, what is the probability that they are selected as president, vice president, and secretary, respectively? So the first thing we want to figure out is how many options we have to begin with, right? So how many students do we have total? 15. And how many students are we picking at a time? 3, right? We're picking a president, a vice president, and a secretary. Do we understand that? Okay, so this is going to be 15 and we're picking 3. So we'd say n factorial. So that's going to be 15 factorial over what? 15 minus 3 factorial. So again, I'm going to have 15 factorial over, this will turn into 12 factorial. How can I rewrite 15 factorial so that things kind of help us a little bit?
15 times 14 times 14 times 12.
13 times 12 factorial. Very good. So now what's going to happen? The 12 factorials will cancel. And so I'm just going to get 15 times 14 times 13. Okay, 2730. So what this is saying is there is 2,730 different ways we could pick these 3 people. Does that make sense? But it's asking us, okay, what's the probability that we pick it as Sam is the president, Valencia is the vice president, and Deshawn is the secretary? Not by 3. We're trying to think of what's the probability that this outcome occurs. So how many outcomes do we have where we would get what we wanted? 1, right? Because this is only going to happen once, right? Because they're not saying, oh, well, any of them could be the president, any of them could be the vice president, and any of them could be the secretary. They're saying, no, Sam has to be president, Valencia has to be vice president, Deshawn has to be secretary. Do we understand that? So there's only one outcome in which we are favorable here. So that means that the probability of Sam, Valencia, and Deshawn becoming president, vice president, and secretary is going to be 1 out of this 2,730. So again, permutations are not probability. That's why we need to be careful there. All right. Are we okay there? I'm assuming we need to do another one together, maybe. We're not ready to do it on our own. Okay, that's fine. So, can I go? So a student identification card consists of 4 digits selected from 10 digits possible, 0 to 9. Digits cannot be repeated, okay? So they're all individual, digits aren't repeated. We want to figure out how many possible identification numbers are there. So how many numbers do I have to choose from? 10. And how many do I pick at a time? 4. Okay, I want you to try from here to get this number on your own. What do we get?
5,000.
5,040?
Yeah.
Mm-hmm.
I don't know.
Okay, so this is our number of possible outcomes. Do we understand that? Now, we want to find the probability that a card generates 4213. So we're trying to figure out the probability that this specific number is the one that's generated. Okay, so how many favorable outcomes do we have? Just one, right? This is one specific number. Do we understand that? So our probability of getting this is 1 out of 5,040. Okay, do we understand that probability and permutations are different? Okay.
Yeah, but it's
Where did you get 4213?
Yeah.
Ah,
It says that number?
um,
Yes, ma'am.
so on the test, when we did probability last class, there was like 3 different ways we do it.
Uh-huh.
Would you take points off if you don't do it like this one way, or can you just choose from the 3?
The table and all that?
Like the table, the tree, and the
Unless I specifically state do it this way, no, I would not take points off.
okay, so
Yeah. If I say like you have to do the tree, then you have to do the tree. But otherwise, no. Okay. Alrighty. Whew, there's a lot of words here. Okay. In a game, you must try to create a word using randomly selected letter tiles. Suppose you select the tiles shown. If you consider the two O's to be distinct, there are 5 factorial or 120 permutations of those letters. Okay. So we're talking about pretty much a game of Scrabble. Do we understand that? Yeah? Okay. And when we play Scrabble, we can have letters that repeat themselves. Yes? Do we all understand that? Okay. In this case, it's O's. So notice that unless the O's are colored differently, so if they're colored differently, they're distinct. Does that make sense? Right? A red O and a blue O are not the same O's. Okay. But if they're not colored differently, we start to run into some issues. So unless the O's are colored or otherwise made to look different, several of these arrangements would look the same. So because there's 2 O's, those 2 O's can be arranged in 2 factorial ways, the number of permutations kind of change. So of O, P, O, L, and S can be written as 5 factorial over 2 factorial. That's a lot of words. So the number of distinguishable permutations of n objects in which one object is repeated is as follows. Okay. So again, we're always starting with that n factorial, right? The problem here is we're starting to have some things that repeat. Yes, do we see that? So to get our number of permutations, we have to take, okay, well, the number of times that first object repeats, factorial, times the number of times that second object repeats, factorial, times the number of times that third object repeats, and so on until we get to a specific number and we're done. All right. This is going to make more sense with a problem. Okay. I promise you it's going to make more sense once I actually do a problem. Are we okay with that?
yeah.
Okay. So we're on a game show and we're given the following letters and asked to unscramble them to name a U.S. river. So we want to select what river do we think it is? Mississippi. Okay. So if you selected a permutation of these letters at random, what's the probability that they would spell the correct answer of Mississippi? So say you're looking at this and you're like, you know what? I don't know. I'm just going to guess. What's the probability that you get it right? So how many letters do we have to begin with?
11.
We have 11.
You can't.
let's guess.
Okay, so we have 11. So that's like our n factorial, right? That's how many options we have to begin with, okay? But do we see how a lot of these letters repeat? Okay, so we need to think about, okay, well, how many times does each one repeat? So let's start with M. Do I have more than one M? No. So that's going to represent, okay, I have 1 factorial number. This is representing that M. Does that make sense? Okay. What about I's? I have 4 I's. Do we see that? So that's represented, I have 4 options for I or 4 factorial. Does that make sense? So this is representing the I's. How many options do I have for S? Also 4, right? So again, this is representing the different places where that S could be. And then finally P. I have 2. Okay, and so this is representing P. So because those letters are repeating, this is how I have to write it, because they could be flipped around. Does that make sense? Right? They're not distinguishable. They're not different. So an S in one place is not any different than an S in another. Okay? Does that make more sense how I got those numbers now? Okay. So this one, unfortunately, things aren't going to really cancel, so we do need to actually use our calculator to multiply this out. So to get 11 factorial, we have to do 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Go. Do it.
Times. You start at 10 or
11.
I think you go to times.
And then what do you put at the bottom?
Yeah, I'm like,
Let's get our top number first.
I did.
It gave me.
whatever that is.
It should be 39916,800.
I got
Well, you're not supposed to do 11 times
168E7.
11.
What the heck?
I don't know. Click up
399.
and highlight it and hit enter and see if it pulls it down.
It's a crazy
Oh, yeah.
big
Okay.
number, dude.
All right.
Okay, I did it.
I did do E7. What's the button?
I don't know. You probably have rounding error. Okay. So then we got to think about the denominator, right? So do we what's 1 factorial?
1 factor?
Is 1.
1.
Right. Do we understand that?
Yes.
Yeah. Okay. So really we need to do 4 factorial. So do we have 4 times 3 times 2 times 1 times 4 factorial, 4 times 3 times 2 times 1
But what?
times 2 factorial. 2 times 1.
Wait, so you do.
Wait,
you
how,
like,
wait,
hold
whoa,
on.
whoa,
Whoa.
whoa, whoa.
Okay.
Slow down.
Okay. Let's all get out our calculators.
You're speaking very
What is 1 factorial?
1
1. So we're going to put 1.
times 4
Times
3
4 times 3 times 2 times 1 for that 4 factorial, that first one.
So you do 4 times 3 times
2 times 1.
times 4 times 3 times 2 times 1.
And then times 4 times 3 times 2 times 1 for that second factorial.
Do you add these together?
You're multiplying.
Oh, more.
And then it's 1152.
It is.
15.
Okay.
And then you divide that. Or
And then that's what we'll divide.
Okay.
What the what?
this is too much.
Yeah. What?
Wait, what?
You were speaking way too fast. You
I'm
gotta
sorry.
slow
You said it
down.
was 1157?
1152.
Oh, the answer, not the time. You got that.
You thought it was a
I
time.
forgot it's too much.
No, Logan made it sound like you were talking about the time.
No.
Okay, so we should get 34,650.
I got 50. Oh, here.
So these are all the possible outcomes, right? Do we understand that? Okay. Are we good there?
Yes.
Can I go?
Yes.
So what's the probability that I get this?
1.
1. Okay. So probability of MISSISSIPPI is 1 out of 34,650. You would think it would be higher, but nope. Okay, can I go? Great. So we want to find the probability that a 7-digit telephone number with the digits 5, 1, 6, 5, 2, 1, and 5 is this specific number. Okay, do we understand that? Okay, so how many total digits do I have? 7. So I'm going to say 7 factorial. Now, what we're really worried here is about the digits that repeat. Do we understand that? Because the ones that don't repeat is going to be 1 factorial, which anything times 1 is just itself. Do we all understand that? Okay, so what digits repeat here? 5. And how many times does it repeat? 3. So we'll have to put a 3 factorial there. Do any other digits repeat? 1. And how many times does it repeat? 2 factorial. So we don't need to include all those other 1 factorials. Does that make sense? Yes?
Yes.
Okay. So now we use our calculator. 7 times 6 times 5 times 4 times 3 times 2 times 1. It is.
What do you say?
5,040. And then see if you can get that denominator as well. $12. Very good. So what's our number of possible outcomes?
420.
420. And what's the probability that we get this specific one?
1 over
420. Very good. Again, this is talking about distinct outcomes. Yes. What?
Why do we have to figure this out?
Yeah. How are we gonna use this in
Because we
real
want to
life?
know our odds if we go on a gaming show, obviously.
What?
And you can't spell Mississippi.
One
When
out of
we can't spell
1,000,005,000.
They want
letters
to-
are
Yes,
right in front of
obviously, I would like to know that if I go on a gaming show. I'm gonna be sitting there going and doing the math in my head before I answer.
That's crazy.
That's gonna take too much time.
That's why
Obviously.
all your
Alrighty.
time
You
away.
are the biggest law.
Well, I'd still like to know the odds.
Okay. So far, you've been studying objects that are arranged in a linear order. Notice that when the spices below are arranged in a line, shifting each spice one position to the right produces a different permutation. So there are 5 factorial distinct permutations. We understand that, moving things over is going to create a different lineup. Yep?
Yeah.
Okay. Now, we can also have what's called a circular permutation, which is objects that are arranged in a circle or a loop. LOL.
Did your earring just fall out?
No, I took it out. I kind of just poked a new hole this weekend. So
You got it just sent it piercing?
no, this one was close enough. So I just took the sharpest earring I had and went. Choo.
Did you cry?
It got through the front part fine, no issue. It's the back side that it didn't want to go through. So I'm trying to fiddle with it and twist it so it stays open. So I don't have to do that again because that's the second time I've had to do that. So I just don't wear earrings consistently
Maybe
enough.
you didn't put it in the right, you didn't put it in steadily.
Oh no, it was. Well, it doesn't matter now.
I
Anyway.
really do want to know who came up with the idea of stabbing your ear and then putting things on it.
Marilyn Monroe.
Maryland Monroe.
Can somebody click that? Alrighty. So we're considering the arrangement of these spices and it's placed on a turntable. Notice that, this is called a lazy Susan. Anyway, notice that rotating the turntable clockwise one position does not produce a different permutation. The order relative to each other remains unchanged. So if I have a little turntable, right, and I have all my spices on it, and I twist it, did the order of those spices change? No, right? We twisted it one position. And so there are 5 ways to kind of rotate it, but the positions still don't change when it's circular, right? So normally we would have 5 factorial options, right? Because we have 5 spices, 5 different ways they could be arranged. Yeah?
That's what
Are we okay there?
Yes.
But we have to account for the rotation, right? So we have to account for the fact that rotation doesn't really count, right? Do we understand that?
Yep.
Because the rotation doesn't produce a different order, right? Yes? Okay. So instead of having 5 factorial options, we have 5 factorial times 1/5, or I can write this as 5 times 4 factorial over 5. Do we understand that?
Yep.
So what's going to happen there? The 5s cancel. So this is really going to be 4 factorial, right? And do we understand that 4 factorial is 5 minus 1 factorial, right? Yes?
Yeah.
So really whenever we're doing a circular one with no fixed place, we do n factorial over n, which is a little confusing. I think the easier way to do it is just subtract 1 and then take the factorial of that. Okay, so when we're talking circular permutations where we don't have any fixed point that we're worried about, we're just worried about it being in a circle, this is how we would set it up. All right, can I go? Okay, so if I'm talking about a charm bracelet here, and they're arranged at random, what's the probability that the arrangement shown is produced? Okay, so again, if I twist this charm bracelet, does it change what the charm order on the bracelet? No, it doesn't. So this is why we're doing those circular permutations. So what would I need to do?
6 minus 1.
6 minus 1 factorial, which is 5 factorial. Which is what?
The probability.
The number. Factorial.
Wait, what was
5
it?
times 4 times 3.
Times 2 times 1. What is that number?
Um.
That's what I'm asking.
120.
120. Okay, but it asked the probability. So what's the probability that this specific
1 over 1.
1 over 120? All right.
Maybe I want to know what's the probability that I'll get a 100 on the test. If I didn't study.
Yeah, how would you do that?
Yeah,
If you
how
didn't
would you
study?
do that?
If you have like, that's
Yeah, I
like,
do that all the time.
it's like psychology.
So,
You have to have more data than that. All right.
What would be
more data. Why don't you just?
You didn't study and your average on test is a 76.
You could ask to do something like
Oh my god.
Yeah,
We should
I
do
know
that.
these ones, but I think I know those ones.
Yeah.
So
Would
I'm
it
gonna
be
take
like
it to
100?
We did that.
Would it like?
Do you guys remember,
There's 20 questions on the
like
test.
back here,
20 questions.
way
on
back
the
here,
test.
you
I'm
remember
pretty
when we
sure I
did
know
this?
18 of them.
Yeah.
the probability that you would guess all of those correctly is 1 out of 65,536.
That's
So it's possible.
It is possible.
No, it is possible.
They're telling
So
you.
let's say you're looking at these 10 multiple choice questions and you go, I don't know. You have a 1 out of 65,000 chance of answering them all right.
So you're telling me I gotta change.
Yeah, exactly.
What if you like had a true or false question like on all of the questions and it was like a 20 answer question and you got them all wrong? Would you still give us 100 because like
No.
you know
Like,
the
managed
right
to get
answer you just
No.
Managed to
No
get
one
them
does
all.
that in real life.
I'm gonna do
that
that.
makes sense if you think
Well,
about
you have fun with that 0 then. Like,
We're gonna
okay. Can I go, please? So we're seated at a party of 4 people at a round table. One of the chairs in this table is next to a window. If the diners are seated at random, what's the probability that the person paying the bill is seated next to the window? Now, do you see how we have a reference point here? Right? So we have this reference point, which is the window. Yes? So before we didn't have a reference point. That's why we didn't count like a rotation as one of ours. Does that make sense? Yes? Okay. But now we have a reference point, so things are a little bit different. So we still have 4 factorial ways to be seated. Okay, does that make sense? Yes? No?
Yeah.
Okay. So what's the numerical value for that?
4
Times 3, which is 12, times 2, which is
24.
24
times 1, which is
24.
24. Okay. Now, again, let's think about this. What if I like sat the person who's paying by the window first, right? So that takes care of my first option. How many options do I have left over? 3. So I have 3 factorial ways. If I sat that person by the window and they're paying. So how many ways is that? 6. Okay. So if the person by the window is paying, out of the total number of options, then there's a 1/4 chance that the person by the window is paying. Does that make sense?
Yes.
Okay. So again, when we have a reference point, that previous rule of n-1 goes away. Do we understand that? Because they're like switching them around changes the order because we have a point of reference. Okay? All right. So the last thing we'll talk about is what is called a combination. So a combination is an arrangement of objects in which the order is not important. So let's say, again, I have like 22 kids in here and I want to pick 4 people to line up at the door. Okay? We're not
Question:
actually doing that.
Why would you find the order if it's not important?
I'm about to explain. Okay. So if I pick 4 people and they line up at the door and the order matters, it matters who's first, second, third, and fourth. That would be a permutation. Does that make sense? Now, if I just pick 4 people and they're all in a clump and the order doesn't matter, that would be a combination. Does that make sense?
Yes.
Okay, so that's the difference between those two. So again, so if we have like, we want to pick 3 packs of 8 different socks for a trip, the order in which the socks are chosen does not matter. 3 factorial or 6 group of socks would be considered different, right? So like the order in which you pack your socks doesn't matter. Do we understand that? Okay, so the way that we do a combination is we kind of write it the same way. Okay, but because the order does not matter, we're actually going to end up with less options, right? So the way we calculate this is we'll still do n factorial. Okay, we'll still do over n minus r factorial, but then we'll also need to multiply by r factorial. So this is that equation when the order does not matter. So all we're adding is an r factorial in the denominator. Do we all see that? Okay, can I go? Alrighty. So we want to find the number of combinations of 8 taken 3 at a time. So again, we have 8 and we're choosing 3. So we'll do 8 factorial over 3 factorial times 8 minus 3 factorial. Okay. What is 8 minus 3 factorial? 5 factorial, right? So we can write that numerator as 8 times 7 times 6 times 5 factorial. And it's going to be over 3 factorial times 5 factorial. So we see that the 5 factorials cancel. Yes? No?
Mm-hmm.
Okay. What is 3 factorial? 6, right? So do we see how that could also cancel with this 6? Yeah. So then it's just going to be 8 times 7. And what's that? 56. So there are 56 ways we could do this.
Will the combinations number always be less than the?
Yes. Yes. Combination should always be less than the permutations. Okay. So for her birthday, Monica can invite 6 of her 20 friends to join her at a theme park. If she chooses to invite friends at random, what's the probability that friends Tess, Guido, Brendan, Faith, Charlotte, and Rihanna, I can't pronounce words today, are chosen? All right, so how many people do we have total? 20. How many people are we picking? We're picking 6, right? So how am I going to write that?
20 factorial over 6 20 minus.
Factorial. Very good. All right. What is 20 minus 6? 14. Okay. So we have 6 factorial times 14 factorial, and I'm going to rewrite that numerator as 20 times 19 times 18 times 17 times 16 times 15 times 14 factorial. Alrighty. So then what's going to happen? The 14 factorials cancel. Now, you could also extend out that 6 factorial and try to cancel some things from there, or we can just let our calculator kind of do the rest. So we should do 20 times 19 times 18 times 17 times 16 times 15.
You would only cancel one number of that number next to 14 would be like
So what you can technically do is we could write this 6 as 6 times 5 times 4 times 3 times 2 times 1, right? Okay. Well, 6 times 3 is 18. Yeah? So you could cancel the 6 and the 3 with the 18 if you wanted to simplify it further. Does that make sense? Yeah, go. Or don't. Just use your calculator.
sound good.
What do we get?
It's like, I don't even know how to say it.
5581440.
I'm talking about the final number.
4, 1, wait. Oops. Did I do something? I got 4651200.
I did not get that. As your final number or as your numerator?
I got 5581440.
Yeah, so
For your final number?
Hold up, let me do that again.
I got 2.
Oh, no.
4000.
Is it 258400?
I did not get that either. Are you putting parentheses in your denominator?
Okay.
Okay. 20 times 19 times 18 times 17.
I got
16 times 15.
5581440.
When I did 20 times 19.
Okay, in our numerator, we should have had 279072000.
0, and then I divided by 6.
6 factorial.
No, that's
6 times 5 times 4 times 3 times 2.
So, finally got 3876.
So 720.
Oh yeah, I didn't do that.
Does that make sense though?
Yeah, I
It's-
think we all like.
It's 6 factorial, not just 6, right?
I did that, but I got this.
Yeah.
Okay.
Okay.
And so what's the probability that we pick these 6 people?
1 out of 387.
1 out of that. Alrighty, last problem. Okay. If 3 points are randomly chosen from those named on the rectangle shown, what's the probability that they all lie on the same line segment? So we need to first figure out how many options we have. So how many points do we have? 8. And how many are we picking? 3. So it's going to be 8 choose 3. So we'd set this up as 8 factorial over 3 factorial times 8 minus 3 factorial. 8 minus 3 factorial is what? 5. So we do 8 times 7 times 6 times 5 factorial over 3 factorial times 5 factorial. Okay. So again, those 5 factorials cancel.
And 6.
And the 3 factorial and the 6 would also cancel. And so it's how many options do we have? 56. Okay. But we want the probability that all of these are on a line. It's not 1 out of 56.
4.
It's 4, right? Because they could be on this line. So there's one option. They could be on this line. That's 2 options. They could all be on this line. That's 3. And they could all be on this line. That's 4. Does that make sense? So really, it's 4 out of 56. And that does reduce. Does anybody know what that reduces to?
1 over 14.
1 over 14. So that would be our probability.
Yeah.
Yeah.